How's that? Better? Excellent. So again, good afternoon, KubeCon. And before we start, I wanted to credit our co-authors because the work we're presenting has been done by 4 people, not just the 2 of us. So I'd like to credit Ares Cohen, Vice President of CloudX and AI at Mellanox, as well as Zhenghui Shi, Principal Software Engineer at Red Hat. Zhenghui, could you stand up, please? Just share yourself to the audience. Ares unfortunately had to catch his flight back home early, so he's not with us. And also, just to finish up the introduction, I would like to make a disclaimer that my work presented here today is based on my own research and ideas, and opinions expressed here are my own and do not represent my employer. All right, so just to get us started, let's talk a little bit about high-performance computing. Just to get an idea what your level of understanding of HPC is, can we have a show of hands how many of you actively use HPC or are familiar with HPC? About a half, very good. For the others, let's start with a quick introduction to HPC and a 40,000 feet overview of the topic. Starting with a definition, high-performance computing refers to systems that, through a combination of processing capability and storage capacity, can rapidly solve difficult computational problems. In my own words, I would describe a typical HPC system as thousands or tens of thousands of high-performance nodes connected with non-blocking fabric, and also a collection of storage nodes connected to the very same fabric. By combination of special software, typically MPI, and the high-performance network with offload capabilities, we can take those thousands of nodes and make them act as one. And this allows us to solve some of the most computational problems that our scientists face. It's important to state that HPC is a great enabling factor for a number of areas of science, starting from medicine, going through engineering, all the way to defense technologies. So for that reason, it's an area of fierce competition between governments all over the world. To back this up, here are some pie charts from Top 500, which is the list of the fastest supercomputers in the world. And from those slides, you can see the main players right now are the US and China. US holding title for the fastest and second fastest supercomputer in the world, China running the third. On the other hand, China holds the biggest share of the overall performance in the top 500 systems. So you can see that the big strategic players are working hard. Bit of feedback. Working hard to gain and keep leadership in the field. And this justifies the importance of HPC for doing computer science. Given we're at the Kubernetes conference, let's spend a few minutes thinking, how can we apply Kubernetes technology and Kubernetes principles to further assist high-performance computing? What is it that we would like to do today that's difficult to achieve with traditional HPC tools such as batch queue-oriented processing? First of all, there are new emerging fields of science, for example, machine learning, and to a degree, biotechnology and bioinformatics, that don't fully fit in traditional batch queue paradigm. Another such area could be cybersecurity. Why is it so? For example, for bioinformaticians, quite often they would like to bring their own environment. They might have certified container images that come from big genomics research centers, and those images are certified to yield repeatable and dependable results. If they were to replicate it in-house, that would break certification. So it's much better for those users to just bring that certified container image and run it on their own infrastructure against their own data. In terms of cybersecurity, I've got users that are aiming to run hundreds or thousands of containers and simulate attacks on IoT infrastructure. It's not something we would let them do on our main supercomputers for security reasons. So they need much higher degree of control and isolation than typical HPC workloads. And that's something that could fit very well in the Kubernetes reality. Now, in terms of machine learning, I've attended quite a few talks today alone where people quote Kubernetes as the de facto standard for machine learning platform. And I tend to agree with this. Many of the tools that my users use depend on building blocks that were developed on Kubernetes. So I think there is something to it. And it's significantly easier for ML experts to run on Kubernetes than to try to retrofit what they do on Kubernetes to a batch queue system. So those three use cases alone, in my opinion, justify an increased investment in Kubernetes from the HPC centers around the world. Just to recap, what are those advantages we're seeking? As we mentioned in the context of bioinformatics, we have the portability and reproducibility advantage. Also, the greater degree of control over the environment that might be useful for cybersecurity. But also, by adopting Kubernetes, we gain access to a very significant and active community that's working hard to develop Kubernetes further. So we go beyond classic HPC and classic HPC tools, and we've got the whole new ecosystem that we can incorporate into our work and toolkit. Now, I believe this goes both ways. So while there is a whole lot that Kubernetes has to offer to HPC users, there are also things that the HPC community can offer the Kubernetes community. First of all, HPC centers are typically very large. HPC systems vary from hundreds to tens of thousands of nodes, so it's pretty impressive scale to run on and test on. So in many ways, we can run into problems faster than usual users would. And similar principle applies to performance. We have really fast hardware and we drive it hard. So we quite often encounter performance limitations before anyone else does. So we can feed that back and work with you guys to make Kubernetes software even faster. So that's what I believe we have to offer. And again, we've got a lot of bright minds and capable developers, so we can make a contribution to Kubernetes if we see that it can fit our needs and help us do more with our fast and large-scale hardware. So if it's also good and rosy, why hasn't it happened yet? What is slowing down adoption of Kubernetes in high-performance computing? In my opinion, it's networking. The requirements for networking, which we see in cloud computing, are very different than networking requirements of HPC. In cloud computing, in my opinion, it's all about security, multi-tenancy, and flexibility. So cloud computing interconnects are typically all SDN. They're very focused on making sure that we can separate different tenants in a secure and resilient manner. We also don't want to be too specific to the hardware we're running on, because the same Kubernetes code base might work on Juniper, Cisco, Arista, anything. We shouldn't really tie it to specific features. So those are the features that, in my opinion, are the most important in cloud computing interconnects. Now, the side effect of that is that the performance might be secondary to all of this. And this is understandable. If we're living in web-centric reality, it shouldn't really matter that much what performance is, because quite often we're being constrained by the client anyway. Now, this is a completely different story in HPC. We can essentially take those priorities we're talking about and reverse them, put them upside down. So, yes, sure, we care about security to a degree, but at the end of the day, performance is king. We want the minimum possible latency, maximum possible bandwidth, and anything that gets in the way of achieving that will probably get removed one way or another. Also, what's very important is that performance needs to be very consistent. As one of the speakers said in the earlier sessions, in HPC, everything runs at the speed of the slowest node. So we need to make sure that there are no slowest nodes, and everything is pretty much equal with performance. So that's something very important. And on top of that, topologies that we use in HPC are quite different than what you see in enterprise networking, because as much as we can, we try to support non-blocking communications. So in extreme case, it can be a factory interconnect, where any node can talk to any node at full bandwidth without any blocking. In more contemporary machines, just because of growing scale, quite often there is blocking, but it's relatively low compared to what you'd see in the enterprise. And yeah, as I said, performance is king. So if there is any security-related functionality that would get in the way of achieving performance, it's probably going to be ignored or limited. So when you look at this, you realize that probably to bring Kubernetes to HPC, we probably need to look into this area and see what improvements can we make to bridge this gap, retain the security and flexibility of cloud interconnects, but introduce the support for high performance that high-performance computing requires. I briefly mentioned using specific hardware for the interconnects and communications. So I would like to highlight one specific bit which is very central to the work that we're presenting today, and that is remote direct memory access, or short RDMA. What is RDMA? It's a transport protocol. It's living in the same networking layer as TCP or UDP. It's much newer, and it's very highly optimized for high-performance computing. What does it do? What can it offer to us and our workloads? Essentially, it enables us to do zero-copy, memory-to-memory communications, completely bypassing the CPU and the kernel. CPU and kernel are only involved to establish the connection between the two nodes. After the connection is established, communication happens transparently, so there is no more need to involve the kernel or the CPU. This is something that gives us excellent latency, which is very hard to achieve in any other way. So that's the first takeaway. So first of all, we're running at low latency, high bandwidth, and also we're saving CPU cycles for the real processing, not for processing communication overhead. Importantly, RDMA was born in the context of InfiniBand physical connectivity. However, in the recent years, it's been ported to Ethernet, so specific Ethernet hardware can also support RDMA. And this is specifically what we're going to focus on today. And with this, I would like to hand over to Feng, who will guide us through the implementation details of RDMA support in Kubernetes.
All right, thank you, Jacobs. All right. To build this solution, we use a number of features from both core Kubernetes and a number of plugins. Sorry. And plugins that we'll talk about each one and what they do and describe them. So we use Multus to enable attaching to different networks. And in this case, it will be a RDMA network. We will use a SR-IOV device plugin to initialize, manage, and allocate NIC resources. We will use a CNI, of course, to plug those resources into the pod. And then we will, of course, also use Kubernetes CPU Manager and Topology Manager for performance optimizations. Okay, and I will talk about each one of them in some detail. Okay, so Kubernetes networking model itself is fairly simple. It has a few principles that must be followed and not much else, right? Those are the ones that are listed there. So every pod will get its own IP address that stays consistent whether it's someone else viewing the pod or the pod itself viewing the pod itself, right? That IP should not change. The IP should be the same. A IP should be able to talk to other, or pod should be able to talk to other pods without NAT, and a node should be able to talk to all pods without NAT, right? So basically, that's in effect in the diagram. The end effect architecture is that you can think of this as a flat IP network, and every pod gets attached to this cluster network, and that works fairly well in most use cases. But of course, in this particular one, what we want to be able to do is attach to another network, in this case RDMA, for a number of my pods, right? Maybe not all of them, but some of them. And so that's where Multus comes in. And so Multus itself is a meta CNI, which in effect calls other CNIs to make attachment to multiple networks. And this can be one or more network. Of course, in the picture, I'm depicting one, but there could be others. So all the pods still require cluster network to follow the same principle that we talked about before, but in addition, I may demand other attachments to other networks. And that's what Multus enables me to do. Multus itself is an implementation of network plumbing working groups, CRD Spec. So we do follow a common API to specify this intent. All right, and architecturally, the way it kind of works is Kubernetes will, instead of calling the regular CNIs that it does, like Flannel, for example, we will replace that with Multus, right? So kubelet will first call Multus as is a CNI, and we will call, let's say, Flannel, and then any other number of CNIs after that, as specified in the pod itself. So in this case, we are going to, of course, use SR-IOV CNI to plug the virtual function into the pod, right? So in effect, the pod will get a ETH0 as always, and then it will get any number of other network attachments like net0, net1, and anything else. Those configurations are stored as CRDs in Kubernetes itself, so you can define them as needed. Okay, CNI, right? So now that we can actually attach to multiple networks, we need a actual mechanism to do so. And we developed a SR-IOV CNI, which in effect, it plugs a SR-IOV VF into a pod. Really what that usually means is the VF will be placed into the pod's namespace. If it's kernel mode, we do support DPTK mode, in which case you'll be running a PMD driver and something like that, right? The CNI does have the capability or the option to manage IPAM if needed, just like others. So that's not, while that's useful, that's not quite sufficient because SR-IOV VF itself is a limited resource and it is a hardware resource. We need a way to manage this resource, and we also implemented a SR-IOV device plugin, which initializes all necessary drivers for the NIC, creates those VFs, and does the allocation, right? So device plugin framework itself is used to do this whole management, and it will also be responsible for configuring things like RDMA mode and things like that. One thing to note is SR-IOV device plugin is NUMA aware, so it does support the node topology manager feature that was introduced in Kubernetes 1.16. So architecturally, the complete picture is on the right. So when the pod gets created, a device plugin will allocate a VF to the pod, and the CNI will take this VF and place that into the pod's namespace, right? That's the entire kind of workflow that this does. Okay, I want to talk a little bit about some performance enhancement techniques in addition to the enablement that we did. So two features I want to call out specifically that are in Kubernetes itself, right? They are CPU Manager and Topology Manager. CPU Manager is a beta feature since 1.9. It is, its purpose, right, is to effectively allocate dedicated resources, right, like CPU, to a container so that a container, right, this is a container level resource, can request any number of dedicated CPUs that it can run exclusively without interruption, okay? CPU Manager is both NUMA aware and hyperthreading aware. It does require a static policy to be set. By default in Kubernetes, it is, it's non-policy, so everything is shared. But it is possible to turn on static policy on a per node basis to allow dedicated CPU to be allocated. Now, Topology Manager was introduced in 1.16 as an alpha feature. It is still alpha in 1.17, but we are working on getting it more mature. So Topology Manager's purpose is to coordinate CPU and devices NUMA alignment. At least that's one of its purposes. So it is able to give hints as to, when I request both CPU resource, especially dedicated CPU resource, and like a NIC, we want to make sure that they are NUMA aligned, right? So that's one of the features that it has. Of course, it's, you can kind of imagine this can also apply to other cases where if I request multiple devices, I may want a specific topology to be applied, right? In that case, for example, two GPUs connected together or something like that. So those are fairly important features that I think would be useful for performance-sensitive application in the future. Okay, so with all of those features together, we get a pod spec that looks something like this. So the Mellanox SR-IOV as our RDMA resource request, right? That says 1 there. So that indicates to our device plugin that I want a NIC, right? The networks annotation for the pod is the Network Plumbing Working Group Spec API, which specifies the additional network attachment definition I want to attach to. So in this case, I say something like RDMA network. So this key refers to a network attachment definition CRD name, which really tells Multus which CNI, for example, I need to call and how do I actually make that attachment to this network. The CPU request right in there, right, CPU 6 in both requests and limits indicates to CPU manager that this is a guaranteed pod and that we need to have dedicated CPUs for this. And of course, the fact that we have both CPU and device requested will also trigger Topology Manager to make sure those resources are aligned on the NUMA node. I think that's it. All right, so Jacob will talk about our lab setup and the performance results that we got.
Thank you, Feng. All right, so now that we know how the solution works, let's have a look at a practical demonstration. This slide is put together just to give you an idea what sort of environment we run this test on. However, the key components are the ConnectX 5 card and the SX6036 switch. Reason being is they both support RDMA. That's the only hard requirement. Other than that, this technology stack would work on a different operating system, different hardware, different CPU architecture without a problem. So let's have a look at the Kubernetes setup. Essentially, we just used a small installation based on kubeadmin with Flannel networking. We then installed and enabled the plugins that Feng described, so Multus, SR-IOV, and so on. And also, we had to do a bit of post-install configuration, both on the hardware operating system as well as Kubernetes. So that involved enabling huge pages, enabling SR-IOV in the BIOS and the card and the operating system, and creating the relevant Kubernetes resources. Feng has run us through the pod definition. I will show you a couple more YAML files to describe the other parts. So the config map is linking the hardware details. So specifically, we've got the vendor and device IDs as well as the interface name in the operating system, and we labeled that with the resource name that we can reference later. And then we create an SR-IOV network, which references this plugin as well. And this puts us in a position where we can run some tests. So I'll just switch over to some demonstrations that we prepared earlier. So in the first demonstration, what we do is we create a pod using the definition that Feng described. So starting with a clean cluster, which doesn't have any pods. Then let's have a quick look at the YAML file that defines the pod. The first important bit is we override the scheduler to make sure we're testing across two nodes as opposed to running on the same node. We reference the network we just created, and we request not less than one and not more than one SR-IOV device for this pod. Then we create almost identical definition for the second pod. The main difference being is we request it to be run on a different Kubernetes node to make sure we're testing the physical network, not just the container SR-IOV implementation. With this, we can go ahead and create the pods. And now we're just ensuring that the pods were created correctly and there are no errors. This puts us in position to fire up the RDMA benchmark and see what performance can we get from this solution. So let's move on to the next video. And this one will go ahead and verify the performance. So again, we're making sure that the containers are running and healthy. And what we'll do is we'll determine the container IDs so that we can exact the RDMA bandwidth benchmark inside those containers. We're doing this on both nodes. Now that we have the container IDs, we can run the benchmark. First, we're doing this on the first node in the server mode, and we'll switch to the second node and run the client. You can see we're referencing the pod IPs, and this is the RDMA benchmark. You can see we're getting over 4 gigabytes a second in containers. We run several iterations of this just to make sure that the numbers are consistent. And we'll talk about the statistics of this in the next slides. So we can see that the consistency is pretty good. First run we can consider a warm-up run, and after that it's pretty much on the dot in terms of consistency. All right, let's go back to the slides. An interesting part that I'll show you in the slides, just in the interest of time, is comparison of Kubernetes pods and the bare metal. So the second number was obtained by running the very same benchmark on the Kubernetes nodes natively without going into the container. You can see that the performance is almost identical. And to look at this further, let's have a look at some statistical data that we've gathered. And here you can see the performance comparison across 200 runs. So the very same benchmarks that you've seen in the demonstration, we left that running for 200 iterations, and then we ran some processing on that, and this is the numbers we got. So we can see less than 1% difference. It's pretty much 99.99% identical between the container and the bare metal implementation. Another interesting comparison is running a bandwidth test on a non-SRIOV container. This is essentially run on the very same setup that we used for the RDMA test. The only difference is for those pods, we haven't requested SRIOV interfaces. So we just used the out-of-the-box default networking provided by Flannel. And this yields less than a gigabit, so over 40 times less than what we achieved with RDMA. With Flannel, obviously, there are other plugins that we could use that would yield better performance, but if we just look at apples to apples, vanilla to vanilla comparison, this is what we get. So you can see that the potential is huge in terms of improving network performance on Kubernetes. And also I want to highlight that we do not only get the bandwidth, but we also get the efficient RDMA transport that can really benefit performance and latency sensitive workloads. All right, so time for some conclusions. From the experiments we conducted, I think we can guarantee that SRIOV-based RDMA support in Kubernetes works very well, and it can bridge that gap between traditional web hosting-oriented applications and high-performance computing applications. Performance, I think the benchmarks that we run and the statistics we've gathered say it all. It's pretty much on par, and there isn't much room for improvement, at least in terms of bandwidth. And with this, I think we can make Kubernetes a really first-class citizen platform to run network-intensive applications. With that, I would like to say that there is a fair bit of future work we see ahead of us. First of all, as I stated early in the slides, we mainly focused on the Rocky implementation for now, just because it's more common to see Kubernetes clusters run on Ethernet, not on InfiniBand. But that doesn't mean that InfiniBand support isn't coming. This is one of the next things we would like to look like, and we need that to support Kubernetes deployments on existing HPC hardware, because HPC centers typically go InfiniBand first. They might have some Ethernet if they need it for specific reasons, but yeah, in HPC, I would say InfiniBand is king. So having the ability of reusing the existing infrastructure would be something very valuable. So that's the first thing. And when we have that going, the next logical goal would be to enable support for high-performance parallel file systems for Kubernetes. So for example, we can do persistent volumes on a file system such as GPFS and achieve excellent performance. And I'll try to show you some of this if we have sufficient time. And also, a couple of time slots earlier, Erez has given an excellent talk with NVIDIA about GPU support. So we believe putting the two solutions together, what we've described with Feng and GPU support, that would create a really excellent platform for ML and other GPU-intensive workloads, just because we can leverage the really fast network. At the same time, we've got the GPUs, and if we combine both, this can yield some serious processing power for suitable workloads. So that's what we're intending to work on next. How much time do we have left?
4 minutes.
All right. So I'll just very quickly run you through the slides illustrating what we can achieve with InfiniBand. This is a snapshot taken from one of my latest systems, which is running on HDR 200. So 40 gigabits is pretty fast, but with HDR we can get close to 200. And you could ask me, what are we going to do with this performance? My first goal would be to deliver this sort of storage performance. And there's a lot of detail in this slide, but what you really need to look at is this. So this is actually a number from an OpenStack cluster that we run that's using parallel file system as a backend. Sorry, that little pop-out tray is getting in the way. But essentially, we'll get 20 gigabytes a second read and 10 gigabytes a second write. And it's in VMs. Imagine what happens if we connect that to Kubernetes. It will only go faster. So yeah, that's something we would like to try in the near future. Just a couple of links if you'd like to explore some of the technologies that we discussed in more detail. And with this, I would like to open the floor for questions. Thank you very much.
We have time for a couple questions.
Thank you. I have actually two questions, right? So basically, I was thinking, how many this SRIOV RDMA device you can support?
With this test, we're using 8 because we had a small environment. I think 63 should work out of the box, but that would be more of a Mellanox question, unless you guys know. I think 63?
I believe so. So the limit is just whatever the hardware vendor can create. That's it.
Okay. I saw you guys using the huge page, 1 gig page, right? Is it already supported in the Kubernetes?
Yes, it is.
Okay. Otherwise, what is I saw you say 4 gigabits, 4 gigabits bytes per second for the testing, right? What is the link speed between those two loads, by the way, physical link?
Sorry, I didn't quite get that.
I mean, between node 1 and 2, what is the network link speed?
It's 40. So that was line rate, yeah.
Okay, one more.
You mentioned that you had some kind of initial results from your InfiniBand implementation of it. Did you do any of the performance comparisons between kind of vanilla Kubernetes on InfiniBand and then the RDMA SRIOV?
And this is still a work in progress.
Okay, all right.
Okay, thank you very much. Please rate this talk on schedule right after, and if you can reach out to the speakers as well, just take the conversation outside as we get ready for the next talk. Thank you.
Thank you. Very good.